Okay, so if our goal is to go through the history of electricity and uh, derive electrical concepts and formulas, starting from basic concepts, basic principles, which is what I would like to do in this series of videos and also on my blog, then um, first thing we need to do is to define some things. We need to define a mathematical vocabulary and a mathematical space in which we can explore these various basic concepts. So we're going to start, and we're going to assume that this page here is our experimental universe, and just ignore the fact that I've written things up here and pretend this is a blank sheet of paper. So first thing we're going to think about is a single point, and we'll label this point P. Now the thing to remember about this single point is that it is merely a mathematical or intellectual construct. It has no analog in physical reality. It's infinitesimally small. It has no width, no height, no length, no depth, and encloses no volume. And I can put an infinite number of them on this sheet of paper. So it has no qualities or parameters other than the fact that it exists on the sheet of paper, and we've given it the name of P. So it's not a whole lot we can do with a single point in space. So we're going to add a second point, and we're going to call this point Q. Now, Q is identical to P in the sense that it is also just another mathematical construct or mathematical concept. It again has no length, no width, no depth, encloses no volume, has no area. It's simply a point in space. But unlike P, now that we have P and Q, we can talk about something else. Not only do they exist on this sheet of paper, but now they exist in relationship to each other. So now that we have 2 points existing in space, we can ask ourselves, what is that relationship between these 2 points? Well, the obvious relationship is distance. So there's some distance, and we'll call it D, between these 2 points. I'm going to call this D sub PQ, just meaning the distance between P and Q. So how do we calculate D? What is the distance between P and Q? Well, one way to do that is to draw a line between P and Q. And then we're going to bring in a new concept, which is the concept of the rigid rod. Now, a rigid rod is just a measuring stick. It's like a ruler, except it's a perfect ruler. It never expands, it never shrinks, it doesn't change over temperature and so on. It's always exactly 1 unit long. Doesn't matter what the unit is, it's completely arbitrary. It could be it could be millimeters, it could be inches, it could be miles, it could be light years. It just doesn't matter. The important thing is that our rigid rod is equal exactly to 1 unit in length. So if I take that rigid rod and I place one end of it at point P, and then I mark off the end of that rod, and then I do that again, and then I do that again, and then I do that again, I can measure the distance between P and Q. And obviously on the paper, these are not all the same length, but pretend that they are. Pretend that I did this perfectly, because that's what we do in math and physics, is we pretend that we do things perfectly. So I took my perfect rigid rod and I marked it off, and I found that P and Q are separated by 4 units. So then I could write that distance between P and Q equals 4 units. Again, what these units are completely arbitrary. What else can I do? Well, see, now that I've got P and Q and a line between them, I'm now in a one-dimensional universe. I have dimensionality. I have one dimensionality. I have length. I have distance between P and Q. So what I can do now is I'm going to extend this line to infinity in both directions. And I'm going to take my rigid rod and just continue on marking off units. And of course, there's P. I'm going to mark off units in the other direction. And these again go out to infinity, so I have an infinite number of units in any direction. And of course, I could have an infinite number of points, P and Q, anywhere on this this line. And we're going to call this line the x-axis, or as Robert Norman referred to it as the not an axis but an axle tree, referring to the old, what they used to call the old axle on an old wagon. So x-axis, x-axle tree, one dimension, goes on forever. So now I want to number these little tick marks I have here. Again, each of them represents units, so I'm going to number them as integers, starting at some arbitrary location. So I'm going to choose this as my arbitrary origin, and I'm going to give that a value of 0. Then these become 1 unit, 2 units, 3, 4, 5, 6, 7, 8, 9, and so on. Then on this side it'd be -1, -2, -3, and so forth. And everybody's seen this. This is just the number line we all learned in grade school. So now that we've defined our one-dimensional universe with the x-axis and with points P and Q, and each of those points having a particular location on that line, and the location is being defined as the distance from the origin. Then we can start talking about something called coordinates. Coordinates are simply the distance from the origin. So we can see that P has a coordinate of 3 units. Q has a coordinate of 7 units. And in general, for any value along the x-axis, we can call its coordinates x, we'll say x of I, where I happens to be whatever we decide to name our point. So P has coordinates x of P, and Q has coordinates x of Q. We could also write that. You could say P exists at point 3, Q exists at point 7. So x of P equals 3 units, x of Q equals 7 units. And again, all this is completely arbitrary. We could just as easily have defined this line so that x of p was, 100 or 23.6 or minus a million or whatever. It's completely arbitrary. The only important thing is that once we choose a set of dimensions in units, we stick with them through our experiment or our equation that we're working on. So now, going back to the idea of distance, we could see that distance from P to Q, of course on our number line it's 7 minus 3 is equal to 4. We can write that as x of Q minus x of P, again these being the coordinates of P and Q, and of course that's 7 minus 3, which is equal to 4. Now, we did this in a single dimension, the x dimension. You can think of this being the dimensionality of length, like a piece of string, an infinitesimally thin piece of string that has no width but infinite length. But we can also do this in more than one dimension.